Okay, good morning. Because of the national test, I have to accelerate a little bit of teaching. So I decided to teach you two sections here. The last section, actually, the last sections of this chapter, because section 4.2 has moved to Math 5. So that would be the last part of this chapter. And those are the product and the quotient rules in differentiation. So you remember that we had some generic rules. Let me repeat them here for you. So if I have a constant number multiplied by a function, and if I ask you to differentiate it, even though that's also a product, but you don't have that much trouble here. So we learned that we just write c and then differentiate my function only and then multiply it by c. And then we had the rule for f plus g. It becomes f prime plus g prime. That's the sum rule or the addition rule. And then we have f minus g prime, which is f prime minus g prime. Okay, so I would call them number 1, number 2, number 3. Today I want to talk about number 4 and number 5 if I want to write them in order. But of course, you already know number 6, which is the chain rule, yes? So this is probably the most important generic rule for differentiation, yes? So you see, I am not talking about a particular function here. Whatever f and g are, these formulas are valid. Today I want to add these two, the product and the quotient rule. So what happens if I want to calculate the derivative of the product, and what happens if I want to calculate the derivative of a quotient. Then together these 6 are complete for us. So you will not have more of these rules in the future. But that table that we were completing so far, you will learn more new functions when you go. But these are the only generic rules that you will have for differentiation. So we want to talk about these two rules today. And then that is the wrong impression if you think that this becomes f prime g prime or this becomes f prime over g prime. So that is not. The formula becomes a little bit more complicated than for the case of the product and the division rather than the addition and subtraction. Okay, and then I hope that you agree that these are really needed. For example, if I ask you, do you know the derivative of x? Every one of you knows about that. It is just 1. If I ask you, do you know the derivative of this? You would say yes. The derivative of e to power x is itself. If I add them and I ask you, do you know the derivative? You would say yes. But if I multiply them, you don't know what to do yet. Yes, if I ask you, what is the derivative of this very simple function? The derivative of x is 1. The derivative of e to power x is e to power x itself. But if I multiply them and I ask you, what is the derivative of this new function? Hopefully you realize this only needs number 4. So you cannot solve this problem using the chain rule for none of these formulas. So you need a product rule for taking this derivative. Yes? So don't think that the problems involved are so hard. This is a very, very simple function, but still we cannot do that. So today we want to learn what is the rule, and the rule is a little bit more complicated than for this one. So the formula is you take the first derivative. You take the derivative of the first function and multiply it by the second function itself. And then you do it the other way around. So you take the derivative of the second function and multiply it by the first function itself and add these two results. If you do that, what you get is the derivative of the product. But of course it would be soulless if I just want to write the formula. Let us understand at least why this formula is correct. Yes? So if I want to prove this one for you, so I would say that let s of x be equals to f of x multiplied by g of x. Okay? My goal is to calculate the derivative of s of x. And of course I want to show that the derivative follows this rule. How should I do that? I have to use the definition of the derivative, nothing else. So if I write the definition of the derivative for the function s, this becomes s of x plus h minus s of x divided by h goes to 0. Yes? Okay, and then hopefully you know by now how to do that, at least for the first step. Minus sign is here. S of x is just this function that you see. It's f of x, g of x. But if I ask you what is s of x plus h, it means that you have to replace your old inputs x here and there by x plus h. That is your new input. So it becomes f of x plus h times g of x plus h. Okay, but the point is that calculating this limit is not as straightforward as the case of addition. Do you remember, for the case of addition, here, let me just write it here and then I will clean it. I had x plus h plus g x plus h, and then I had minus f of x plus g of x, and then divided by h, yes? For the case of addition, I had this, but this can be simply decomposed into two fractions. I can immediately write it as f of x plus h minus f of x plus g of x plus h minus g of x, and then divided by h. When I divide this part by h, it gives me the derivative of f. When I divide this part by h, it gives me the derivative of g, so I get this formula immediately. But the algebra becomes a little bit more complicated here, you see. I want to find a way so that this combination and that combination somehow appear here. Because you see that I want to have f prime and g prime somehow in my calculation. And of course you see that you will have some extra terms. So what can I do here? So that was just the motivation. So if I want to continue, I just want you to understand why it was easier to calculate the derivative of the sum, but it becomes a little bit more involved if I want to calculate the derivative of the product. Because the algebra becomes a little bit harder. So, but anyway, I need to have this combination somewhere. I also need this combination somewhere. But of course, I cannot change it unless I compensate for that change somehow. So let me just tell you this. F of x plus h, g of x plus h. I want to have minus f of x. So I would write it minus f of x times g of x plus h. And then I add f of x, gx plus h. I will explain in a moment. So minus f of x, g of x. So first, I hope that you agree that at least this equality is sound, yes? It makes sense. Because what I have done, I have subtracted this and I have added the same thing. So I have done nothing. Yes, this and that are cancelled. What is left is this one minus that one. So if I say that, do you think that this equality is valid? You would say yes, because this fraction is indeed the same previous fraction. Yes? But I have added this term and subtracted that term. Yes? But then it becomes a little bit clear why I did this. Because I told you that my motivation is to get this combination and this combination somehow in my fraction. And this is possible now. Why? Can you see that yourself? Give me comments. So what can I write in the numerator? I want to have this combination somehow appearing in the numerator. What should I do? I want f of x plus h minus f of x. So what should I do? Come on. What should I do? What should I do? Yes?
If you factorize
g.
g.
Thank you. You have to factorize this, yes? And then factorize that. Factorizing is still hard for you, I don't know why. But you take this out, so this becomes g of x plus h. What is left for me? F of x plus h minus f of x. Is that the combination that I need? The answer is yes. That's one of the combinations that I need. But what can I do here? I can factor f of x out. Yes, so it becomes plus f of x, and then I will have g of x plus h minus g of x. Yes? And then h goes to 0. But what can I write now? I can separate them. Instead of writing everything and then divide by h, I can divide this by h plus this divided by h. So what I can do, I can write the limit of, let me write it in this way, g of x plus h multiplied by this fraction f of x plus h minus f of x divided by h plus, I write f of x here, and then I will have g of x plus h minus g of x divided by h, and then I have this. H goes to 0. Okay, take your time. Do you understand what I have done? So I have divided this part by h and that part by h separately, but I have written this in the opposite to this fraction line. So hopefully you agree with me. What I have written there is exactly what is here. Yes? But now I am sending h to 0. This limit I don't have any problems with. What is this limit when h goes to 0? It is nothing except f prime of x, yes? This limit I don't have any problems with. This becomes what? G prime of x. But I'm also sending h to 0. This is also depending on h, yes? This part does not depend on h. This part, and that part all depend on h. I don't have any problems here and there because I know that if I send h to 0 for this fraction, I get f prime. For that fraction, I get g prime. But what happens if I send h to 0 here?
G of x.
This becomes g of x. But of course, it is more technical than that. But at this level, forget about that technicality. Yes, you can write g of x. And then if I write it down, this becomes g of x. Because if you want to write this, you need to guarantee that this function is continuous at point x. And this is guaranteed by another theorem. So forget about those technicalities, you can write that. So you can write g of x multiplied by f prime of x. And then you have f of x multiplied by g prime of x. And hopefully you agree that that's exactly the same formula that I have written here. F prime times g, g prime times f. Yes, so that is the formula that eventually you can go to sleep very calmly in the area. You couldn't sleep if you don't know this formula, I think. Yes, but now you can relax. Okay, so how we can calculate, how can we use it? This is very, very simple. So if I give you this function now and I ask you to differentiate it, of course the name of this function I have chosen is f, don't get confused. I have this function f, this. If I ask you to differentiate it, be careful. Still, I might see some of you take this one and that one separately. I have seen many students write the answer to be e to the power x because they think the derivative of this one is 1, the derivative of this one is e to the power x, and then multiply. That is not correct. So what you have to do, you realize that this is a product, so that would be the product rule. And it means that this becomes the derivative of the first part multiplied by the second part itself plus the first one multiplied by the derivative of the second one. So that you have to write. And the derivative of x is now 1, so it becomes e to the power of x. The derivative of e to the power x is e to the power x itself, so it becomes x e to the power of x. So you see that if you do it in the wrong way, you just get the first term. You do not get the second term. But the whole expression should be written there as the derivative of this function. So is that clear? Okay. So then you can solve a lot of problems. Now we can combine a lot of problems together, so I don't want to go through it. Because, for example, if I give you this sine of x multiplied by cosine of x. Let us differentiate this function. This, I want you to understand that you couldn't solve this before you know about the product rule. This is important. But then now that you know it, you can immediately calculate the derivative. So the derivative is what? The derivative of the first one multiplied by the second one itself plus the first one multiplied by the derivative of the second one. Yeah. Okay? And then I don't know, do you remember the formulas? The derivative of sine is cosine. And then multiplied it by cosine. And then here I'll have to repeat sine. But the derivative of cosine, do you remember? Minus sine. And then cosine times cosine is cosine squared x. And this becomes minus sine squared x. So that is the formula. But of course, in this case, you could do it, in this particular case, you could do it simpler. How should I do that? Let me change my color. You don't have to do, but this is the lesson today. But if you have a little bit of geometry in your head, so f of x becomes 1/2 sine 2x. Yes? And then you can use the chain rule to solve that problem. Because sine 2x, if you remember, is 2 times sine x cosine x. That 2 will cancel this 1/2 and I get this function. So it is completely clear that I can write this function in this form. Then I don't need the product rule. Because what I have here is 1/2 and I can use the first rule. Okay? And by the way, the first rule is also a product rule. Yes, do you see that? Can I use the product rule for this one? Of course I can, but that would be stupid, yes? Because then I am making things harder for myself. But if you want to, you can do that. CF derivative, it becomes the derivative of the first one multiplied by the second one itself plus the first one multiplied by the derivative of the second one. But the derivative of a constant is 0. This is why you don't see it and you just see it like this. So, but that is a very special case of the product rule, which we really don't need to bother about the product rule at all. We can do that. But if you do it using the product rule, of course, mathematics should be consistent and you would get the same answer. Okay, if I do it like this, then I need the chain rule. So I need to take this u in my head and then I differentiate it. So f prime of x becomes what? I take this 1/2 here and I take the sine of u derivative. Sine of u becomes cosine of u, but it is not finished. I have to multiply by u prime. But u prime is 2. That 2 will cancel that 2. Then I will get cosine 2x. Okay, one I get this one, and one I get this one. Do you think this is wrong? Yeah? They are the same. Yes? That's the formula for the cosine of the double angle formula, and that is 1. So here might be the chain rule is easier. But if I change x here, for example, to 2x, then the product rule is the only way. Because sine x cosine 2x, that's not a nice combination. Okay. We can solve a little bit more of these examples, but I want to finish this lesson today. But before that, I want to ask you, you are supposed to ask me one question now. What is your question? Okay, what's the question? Don't hesitate, ask. Yes?
Is it the chain rule version?
No. Not the chain rule version. No, these, you don't have any chain rule versions for these generic rules. Chain rule version are only for particular functions. Yes. What's your question?
Of course, about the division.
No, the division comes next. But now, for the product rule, you should have a question.
We should have a question.
How is that possible? You don't have any questions.
Is it something to do with the theorem you talked about?
No. It's a very natural question.
Allt här ser bra. Vänta, vad händer?
Yes?
Any limitation?
No. Now, what do you mean by limitations? I don't know.
Using the formula.
No.
Oh, just
No, very natural question.
It looks good.
Okay, let me guide you through that natural question. So, if I give you this function, and I ask you to differentiate it, can you do it or not?
Yes.
Yes. Which rule are you using?
Product rule.
No, this is not product rule. The addition rule, the sum. Okay, but the addition rule originally is written for how many functions? 2 functions. So, but this is 3 functions. By the way, if you want to prove it, you can use mathematical induction. So you can show that I can extend that to higher number of functions. So that also works, should be a question here. What happens if I have the product of 3 functions, not 2 functions? Then how should I do that? Isn't it natural?
Yeah, it is.
It should be natural. So if I give you x multiplied by sine x multiplied by ln of x, and I ask you to differentiate this, which is of course a function, but it is not the product of 2 functions, it's a product of 3 functions. But how should I do that then? Yes?
Find the product of 2 of the functions first, and then
You need to guide me exactly. Okay, if you want to answer
like
that.
first take the product of the x times sine x, and then multiply that by ln of x.
Do you believe in that? So you are saying that.
I think.
So you are saying that if I want to differentiate this function, so what you are saying, if I understood you correctly, otherwise you correct me. So x times sine x times ln of x. So what you are saying is to do what? Can you tell me f prime of x? I want to write it down. So what should I write?
I appear to be wrong.
Yes. But how should I do that? The idea was not totally wrong. The way you express it was wrong. So how should I do that? The product, this is the product of 3 functions, but I can view it as the product of how many functions? 2. Yes? By the method that you mentioned. So it means that I put this in the pair of brackets and consider it one function, and then this I consider it the second function. So it was the product of 3 functions in the beginning, but I myself can view it as the product of 2 functions by putting them in the pair of brackets, for example. And now if I ask you what is the derivative of this product, this will play the role of your first function, this will play the role of your second function. And then it becomes the derivative of the first function multiplied by the second function itself plus the first function itself multiplied by the derivative of the second function. Yes? This I don't have any problems. Yes, it becomes plus x sine x. I don't know if you remember or not. You can just review, or you can just refer to the table. The derivative of ln of x is simply 1 over x. But again here there is a prime left, so the process is not finalized yet. So I have to continue with this one. So I copy and paste this part. But then again this is a new product rule, but the product of 2 functions only. Yes? So what I do, I open a pair of brackets here, and what I do, I would say the derivative of the first one multiplied by the second one plus the first one multiplied by the derivative of the second. That is the way that you have to do it. Yes? So it becomes very, very messy if I have more than 3 functions. So you have to do it all the time. So you have to have, I don't know, for 4 functions what we can do. And let me write the formulas later. So I continue this, the derivative of x is 1 times that, it becomes sine x. This becomes the derivative of sine becomes cosine x. And the whole expression should be multiplied by ln of x. This x here and that x there are cancelled, so I will get sine x. And of course you multiply them, so it becomes sine x multiplied by ln of x plus x cosine x multiplied by ln of x plus sine x. So that would be the derivative of this product. Yes? So I view it as 2 functions. But instead of doing that all the time, we can do it once and then find a pattern how it will go, and then you can guess, and then you can use it if you want to. Yes? So if I have 3 functions, f, g, and h, and I want to differentiate the product. So let me write here to save some space. So if I want to have f, g, and h, and I want to multiply them and then take the derivative. So what can I do? I can view it as 2 functions again. So it becomes fg as 1 single function multiplied by h totally derivative. So it becomes the derivative of the first part multiplied by the second part itself plus the first part itself multiplied by the derivative of the second. And then what happens here if I do this product rule again, f prime g plus fg prime, totally multiplied by h, and then I can remove the pair of brackets, I don't need it anymore. and then I distribute it inside. So it becomes f prime gh plus fg prime h plus fgh prime. Now you see the pattern. Yes, it is easier to see the pattern here. So if I have fgh prime, it becomes f prime gh, fg prime h, fgh prime. So then I think that now you can guess if I have more than 3 functions involved. What is your guess for the answer? F, G, H, S, all of them are multiplied, and I am interested in the differentiation. So what happens for this product? It becomes F prime, but everything left alone, and then plus F, G prime, H, S, plus F, G, H prime, S, plus F, G, H, S prime. That actually would be a very hard calculation because you have to do it, but that is it. So you have to do it if you want to differentiate more than the product of more than 2 functions. Yes, is that clear? So that was the natural question I was looking for. Okay, now before going to the next example, I want to introduce the next question mark, and then we can have some examples together. Okay, so this one, because the space is not enough, so let me change my color, not because it is important, because I want you to see it. And this becomes even more complicated than that. So if you have f over g derivative, the rule is the derivative of the numerator multiplied by the denominator itself minus the numerator itself multiplied by the derivative of the denominator, but then divided by not the denominator squared. Okay, and that's a very, very bad formula. I recommend you to avoid this formula whenever you can. But of course, sometimes it is not, it's inevitable, you have to follow it. So you remember, I had some examples for you. You differentiate fractions, and you didn't know about the quotient rule yet at that time. So it means that still continue doing them in that way, not using the quotient rule. Okay, but now why this formula is correct? So my question is that how can I calculate this f over g prime? I want to confirm that this is indeed the case. What I wrote there is correct. One way, of course, is to start from scratch again using the definition of the derivative, which becomes a little bit messy. But we can do a better way, be more clever, yes? How can I do that? Because every quotient can be viewed as a product. Yes? This is important to remember. So, if I want to start from scratch, I have to write these kind of things, but for fractions, which becomes harder. And it is doable. But let us choose the alternative. So if I ask you, how can I calculate the derivative of a fraction? You can say that I can view the fraction as a product. How? How should I write that? So f over g prime is what? Is f times 1 over g prime. Yes? Okay, let me be more specific here. So let me write the x's here. You will have troubles. Yes, let me write it like this. F of x over g of x prime. The first thing that I do, I write f of x multiplied by 1 over g of x totally prime. And then I bring it up. It becomes f of x, g of x to the power of minus 1, then prime. Yes? I hope that you understand what I have written here, yes? But now the point is that this is no longer a quotient rule. That is the product rule that we know how to do with it. So what I can do, I can differentiate the first part and multiply it by the second part itself according to just what we learned right now. Yes, we don't need this. Minus 1. But it is not finished. I have to write the first one, multiply this. I want to test your understanding for this part. Yes? So take your time to see if there's something you don't understand. What I have done, this is hopefully clear. There is no difference between f over g and f times 1 over g. And instead of 1 over g, I have written g to the power of minus 1. And then if I ask you what is this is a product now. And I want to differentiate a product. According to the rule that we learned today, it's the derivative of the first one multiplied by the second one itself, but plus the first one multiplied by the derivative of the second. Yes? Here, I don't have any problems. If you want to, I can bring it back and make it positive 1. So let us do that. Okay, so it becomes f prime of x. I will bring it back to the denominator and make it g of x. Yes? So that is the first one. But my question for you is that how can I deal with the second derivative in the second term? What rule is that if I want to do it? So the rules are here actually, so let me raise the board. So whatever you need is on the board, but tell me which rule is that for calculating the last one. So here, let me write plus f of x, but the question mark for you is here. What can I write for that and why? Yes?
Chain rule?
Chain rule, yes, exactly. But can you tell me why? How?
Using g of x as u.
As u, exactly. So if you take this one to be u, then what you have is u inverse. And then you need to take the derivative of this. But can I do that? Yes. Minus 1 goes down, u to the power of minus 1, but is it finished? No. I have to multiply by u prime. That is the chain rule, yes? So then what happens? It becomes minus u to power minus 2 multiplied by u prime. Minus 1 is minus 2. Minus 1 multiplied by anything, it becomes the negative of that. So it is exactly this. Thank you very much. So in this stuff, instead of this question mark, I can use the chain rule now. So what can I do? I have a negative sign, so let me write negative. U is g of x, so it becomes g of x to the power of minus 2, but it is not finished. Multiplied by u prime, so it gives me g prime. Exactly. Understandable or not? Okay, and then you have to do some simple algebra. Because that is finished. This is your derivative, but it's ugly, yes? So let us make it more beautiful, even though that's also ugly, yes? But anyway, it's better than this one. So what I have to do, it becomes f prime x g of x, and then minus positive multiplied, it becomes negative. And then instead of power minus 2, I bring it down, it becomes f of x, g prime of x, but I will take this to the denominator, so it becomes g of x to the power of 2. And then what I need to do is to take the common denominator. So what is the common denominator here? It is g of x to the power of 2, so it is g of x to the power of 2. This one divided by that one gives me 1 factor of g of x. I multiply it in the corresponding numerator, so it becomes f prime of x g of x. I have a negative sign, and this one divided by that is just 1 times. I multiply it here, and this is your formula. So that is the reason why the quotient rule works in that way. The derivative of the numerator times the denominator itself minus the numerator itself times the derivative of the denominator is squared. Yes? So in principle, you can follow the same rule, because I have seen some students don't like to use this, but that is inevitable, I would say. Don't think that if you write it as a product, it becomes simpler. No, you have to do all those processes. So what I can do now, I can give you an example. So here, if I ask you y is equal to x plus 1 over x minus 1, then I ask you what is y prime. Yes? This is something that you can do right now, but you couldn't do before. Yes? So what should I do? It's a fraction, and it is an inevitable fraction. Of course, you can say that I can write it in this form. That is, if you want to follow this, you have to actually go through the proof for this one. which I don't recommend. If it is inevitable, use it. But if it is not, you can avoid that. So here, it's inevitable. I have a fraction. I cannot write it in a way that is not involved with fractions, so I have to use the quotient rule. So be patient then. So y prime is what? The derivative of the numerator multiplied by the denominator itself. The derivative of the numerator multiplied by the denominator itself minus the numerator multiplied by the denominator derivative. But not divided by the denominator, divided by denominator squared. So I'm using the formula, yes? Is that understandable? And then you have to calculate until there are no primes left. So the derivative of x plus 1 is very simple. It is just 1, so it becomes 1 times x minus 1, which is x minus 1. The derivative of x minus 1 is also 1, so multiplied by that, I have a negative sign, so it becomes negative x negative 1, divided by x minus 1 squared. And then what happens, this x and that x are gone, so this becomes minus 2 divided by x minus 1 squared. So that would be the derivative of this function. Okay, so let me see if there is something that I have missed. Not actually, so everything is covered, and then of course you have to do some practice. Okay, so let me just tell you something. We can solve some of these problems. To remind you, we have a little bit of time, so I will give you a little time to practice yourself. But before that, let us just do some calculations. Let me bring that one down. So I clean all of them. Hopefully you remember them. Okay, so for example, if I give you this, y equals to 2x squared plus 1 divided by x, and I ask you to differentiate this, this is one of those cases that you can avoid the quotient rule. It doesn't mean that you are not allowed to use the quotient rule. If you use the quotient rule, definitely you will get the correct answer if you do it right. But this is possible whenever you have one single term in the denominator. It is better to divide them separately rather than using the quotient rule. Here I want to do it in two ways. I want you to feel that they are the same. Which one is easier? In principle, I can give this in a Math 3C exam. Because if I ask you to do this, then you write it as 2x squared divided by x plus 1 over x. And I'm writing all the details. You can do it faster in your head. So this becomes 2x, and then I bring it up. It becomes x to the power of minus 1. Now I differentiate as a Math 3C student. So this becomes 2 minus x to the power of minus 2. If I insist to make it positive, then it becomes this. So that is the derivative. But if I want to use the quotient rule, I will make life harder for myself for no reasons. Then I take the derivative using the quotient rule. It becomes the derivative of the numerator multiplied by the denominator itself minus the numerator itself multiplied by the derivative of the denominator divided by the denominator squared. And then what happens? The derivative of this is 4x multiplied by x is 4x squared. The derivative of x is 1, multiplied here becomes the same, but I multiply a negative sign in, and then divided by x squared. So if you see, it becomes 4x squared minus 2x squared, which is 2x squared minus 1x squared. So you get this answer, which is exactly this answer, yes? Because if you divide 2x squared by x squared, you get 2. If you divide this by that, you get this one. But of course, if you are using the quotient rule, might be naturally you will stop there. That's completely okay. But if you use this, you stop here. I would rather to do this. And by the way, you see that all these things that I have written, I could avoid. because it was so simple. So the derivative is very simple. So if it is possible to avoid the quotient rule, do it. Otherwise, you have to use it. Okay? And this is something that I want you to learn. And here, for example, there is another method to do this, and I told you in the previous lesson, and that was, this is not in the book, but if you want to use it, you can use it, and I accept that. So you can use logarithmic differentiation. So what I can do here, I can take the y, it doesn't, this is still the best method for this simple problem, but let us just compare the methods. You take absolute value from this, so it becomes this. And do you remember, logarithmic differentiation tells you that take ln from every side. So this one becomes ln of absolute value of y. This becomes ln of a fraction. So it becomes ln of the numerator minus ln of the denominator. But we had this before. Do you remember? Ln of absolute value u prime is u prime over u by the chain rule. So I take the derivative of this, it becomes y prime over y. The derivative of this, it becomes 2x squared plus 1 in the denominator. The derivative of this is 4x. And then it becomes minus 1 over x. But I am looking for y prime, so I multiply everything by y. Yes? So this means that y prime is y multiplied by 4x, 2x squared plus 1 minus 1 over x. But of course, I have to write this expression for y, and then it becomes 2x squared plus 1 over x multiplied by 4x over 2x squared plus 1 minus 1 over x. And then, of course, that is it finished. But if you want to compare the results, you can multiply this thing in. This one and that one are cancelled. I have some mistakes somewhere. Yes, can you see that? Because the answer should be... No, that's correct. So I multiply that in, this one and that one are cancelled, this one and that one are cancelled, so it becomes 4. And then I multiply this in, so it becomes 2x squared plus 1 divided by x squared. But if you simplify that, 4x squared minus 2x squared becomes 2x squared minus 1 over x squared, and you get the same answer. But you see that this is even lengthier than this one. This is the simplest way. But this is very strong tool, I will tell you. For example, if I give you such a horrible function, I don't know. Yeah, that's it. For example, if you want to do this using the quotient rule, it is very, very hard. Yes, it is lengthy, not hard. But using the logarithmic differentiation, it becomes much simpler, at least doing the operations. How? Because what you do, you take absolute value, and then you take ln. But ln becomes very simple in this case, because this becomes a product, and this becomes a quotient. Ln of a quotient is the ln of the numerator minus the ln of the denominator. Yes? So ln of x over y is ln of the numerator minus ln of the denominator. So this becomes ln of the numerator minus ln of the denominator. But the numerator is a product, and if I have ln of x dot y, it becomes ln of the first one plus ln of the second one. And if I have a power on my x, the power will go back. It becomes this. So these three combinations of formulas makes this a little bit simpler. Much simpler than the quotient rule. But then in that case, that would be the optimal way to do it. So then what happens? It becomes 10 ln of absolute value of x plus 7 ln of absolute value of x squared minus 1 plus 8 ln of absolute value x squared plus 1, but minus 7 ln of x squared, 5x squared plus 1. You see, but none of them are hard to do. Because there is a very nice rule for the derivative of ln. So then I take the derivative of that one, it becomes y prime over y. The derivative of each term is very simple using that. And then what you need to do is to multiply by y at the end. So you don't have such a question in the book, but I want you to see that this is at the level of your understanding, so you really can understand. If you want to understand it better, you can do it at home, and if you have questions, please come back and ask me. First of all, you need to understand why this translates itself to this way of writing using these three formulas. And now you take the derivative from this one, it becomes just y prime over y. Taking the derivative of this, and that are very simple because the formula is very simple. And then what you need y prime. So I need to get rid of y. So at the end, I multiply everything by y, and that becomes my derivative. Okay, I see one question in the book. We had it before, but then I told you that, sorry, I cannot solve it because we don't know the product rule. I want to do it now, okay? And that question was this. So let me just remind you. If I have this function is called, c is constant. This function is called a power function. Its derivative is what? cxc minus 1. If I interchange them, c goes down, x goes up, this is called exponential function. And we also discovered the formula for this. The formula was c to the power of x ln of c. Yes, do you remember? But now the question is that what happens if I have x to power x? This is neither called an exponential function nor a power function, but that's just a function. And I even don't know how the graph is. We can also use GeoGebra to see the graph. But this makes sense only if x is positive. Now the question in the book is that find the derivative of this function. Okay? So it means that I cannot use this, I cannot use this. So I have to find a way to find the derivative of this function. And none of the methods will work. The rules that I have, I don't know, quotient rule, product rule, whatever we have doesn't work for this. So even though this looks very, very simple function, but it is a little bit hard to understand how to do that. And again, the method is what is called here. It's called logarithmic differentiation. Yes? So what you do, this is my goal. My goal is to find the derivative of this function. So my goal is to find y prime. Instead of doing that, I take ln of y. And I don't need to bother about absolute value in this case because x is supposed to be positive. So x to power x also becomes positive and y is positive. Yes? So then it means that this becomes ln of x to the power of x. If you tell me that y is, then ln of y is also ln of x. But then, because of the rule that I wrote here, this p can go to the back and be multiplied by ln of x. So then I write it one more step. This becomes x times ln of x. But now I can differentiate this according to the product rule that we learned today. So I differentiate the left-hand side and equate it with the derivative of the right-hand side. Because if you tell me that two functions are equal, the derivatives should also be equal. And then the derivative of this we know. It is y prime over y. The derivative of this we learned today. That is the product rule. So it becomes the derivative of the first one, 1, multiplied by the second one, which is ln of x, plus the first one, x, multiplied by the derivative of ln of x. The derivative of ln of x is 1 over x. Multiplied by that x, it becomes 1. But I am looking for y prime, so I have to make y prime alone, so I multiply by y. So then it becomes y prime is equal to y multiplied by ln of x plus 1. But this is not a common way to write, because if I give you a function in x, I expect you to give me the derivative in x. So it means that it is a very bad notation here. So what is y is x to the power of x. So y prime is x to the power of x, ln of x plus 1. It's a very strange way of differentiation. So that's the derivative of this function. But that is one question in the book. So if y is equal to x to the power of x, what is the derivative of this function? And if you don't know this method, there is no way for you to do that. Okay? So from now on, you can have it as a rule of thumb. If I have variables in the base and in the exponent, and if you insist to differentiate it, there is only one way, and that is logarithmic differentiation. For example, if I want to give you another example here, I can ask you to differentiate this function if x is positive. So you see, none of the rules that you have learned so far will work for this. But you need to understand it yourself. How do you understand it? By realizing that the base and the exponent are both variables. Whenever this happens, it means that none of the rules that we had before will work. So you have to remember this trick of logarithmic differentiation. And that is what we have to do. We take ln of y equals to ln of this. But you need to remember a nice property of ln. You can take this power and put it back as the multiplicative expression. So this becomes cosine x multiplied by what is left for me is ln of x. Then I differentiate the left-hand side. The left-hand side is always y prime over y. But the right-hand side turns out to a product rule. This becomes the derivative of the first one. Do it in your head. It is minus sine x multiplied by the second function itself plus the first function multiplied by the derivative of the second function. If you refer to the tables, if you don't know them by heart, this is the case. And then you remember your goal is to find y prime, so you have to make y prime alone by multiplying everything by y. So if you don't mind, let me continue here. So then it becomes y prime is equal to y times this combination. Cosine x over x. But then don't forget to replace y, because it is odd. If I give you a function in x and you return back this formula for me, it's a little bit odd. So instead of y, I know what is y. I put it back. So then it becomes y prime is equal to x cosine x and the rest of the story. So minus sine x, ln of x, and then plus cosine x over x. But the point is that to understand where you have to start this. When you start, the rule of thumb is when the base and the exponent are both variables. In that case, you can start this way. Yes? Okay, let me ask your understanding here. If I give you this, so what is the derivative of this? What type of function is that?
Power function.
It's a power function. But the exponent is a little bit odd, but it's a constant. Yes? So if you want to differentiate it, just use this rule. Yes? So sine 23 degrees goes down. I'm not taking the derivative, so it doesn't matter if this is degrees or radians. And then I can write x to the power of sine 23 degrees. Whatever it is, I don't know, minus 1. That's the derivative. But you need to understand that we have these formulas, but there is no particular formula if both of them are variables. You have to do them case by case by logarithmic differentiation. Yes? Is that understandable or not? Okay. Anything that I have missed? Nothing actually. So everything is covered. Then you can start practicing. Yes? I can update the Google Classroom for you. So this chapter is finished now. Because 4.5 is gone for Math 5. Yes? So differential equations are only for Math 5 now. Yes? So this chapter is finished. Sooner or later you have to expect an exam coming. Do you want to have the same exam, on the same day?
No. What?
Yes. Math 5 and 4 together. Yes. Is it good?
No. We already have
That would be easier for me, yes? Because we have to hurry a little bit. Okay, thank you very much. I will update the Google Classroom now.